All right, so welcome back. As promised, we are going to start by taking a few minutes to make sure that you have an opportunity to fill in the evaluation form. So I'm going to give you maybe until, let's say, give you 7 minutes. So at 22 past 9, we will continue the lecture. So please, if you haven't already done so, open the form. You will find it in your email sent a few days ago, and you can fill it now. Thank you. All right, so is everybody done? Who needs more time? Not in the lecture hall, on Zoom. Does anybody need more time, or has everybody completed the form? I don't see any complaints, so we'll just proceed with the next lecture. All right. So this is almost the end of the semester, actually, because we have already done a lot. I need to put it in perspective so that you know exactly what we are still missing and why we are missing it. We are coming at this from two sides. The first side is via document stores, and the other side is via Spark. On the side of document stores, what we have is some system in which you can pour data, and it's very good at returning documents very quickly and also making complex queries in an aggregated way. So it has plenty of advantages. However, it doesn't have a query language. You have this application programming interface, API, and you can do it in JavaScript. There is also a Python version. There's many different languages, but it's not a query language. It's just a programming interface, and that's not as convenient as a language like SQL. So I assume that many of you probably would find the SQL version easier than the JavaScript version, right? Who finds the SQL version easier to write? Okay. But the problem is that SQL doesn't work, because SQL was never designed for nested and heterogeneous documents. So sometimes I can give you a SQL equivalence when the data is structured enough that it actually is looking more or less like a table, but SQL in general is not suitable for that. So we need something different that is an extension or more powerful than SQL to work on nested heterogeneous data. So this is where we are. It's amazing what we've done, right? Look at it. We have stored our documents. We can do it on HDFS, on S3, on Azure Blob Storage, on your local drive, on your own laptop. We've seen encoding, even that we didn't spend too much time on, but it's the idea that you can put text into bits so that computers understand them. We've looked into syntax, XML and JSON for nested heterogeneous data, but it also works with CSV for tables and so on. We've looked at data models. So we've seen that when you denormalize tables, you get collections of trees. So this is why trees are so fundamental in big data, because you can nest data, you can have heterogeneous data with collections of trees. So we've looked at data models. Then we've looked at validation with XML schema, with JSON schema, with JSON, and there's many other technologies out there. And we did have a realization. We had the realization that if you take any collection of trees, it can be a big mess. But if you take a collection of trees and you validate it against a schema that specifies some structure under certain conditions, that collection of trees can actually be nicely drawn as a data frame. Who remembers data frames? Right? It's a generalization of tables that also allows for nested structures. So you can have nested arrays of objects and so on. But if you do have a structure like this with these patterns, you don't need to draw trees anymore. You can directly draw with vertical and horizontal bars. All right, so this is a data frame. Then we saw that we can process data at very large scales with MapReduce and with Spark, but we saw it's pretty low level, right? Spark and MapReduce. It's also not a query language, Spark and MapReduce. These are also application programming interfaces, something you need to do in Python or in Java or whatever. So the Spark API, application programming interface, is just like the MongoDB API. So it's not a query language, so it's not that intuitive. Then we've looked at indexes, not with Spark and MapReduce, of course, because they don't have indices, but MongoDB has them. So if you have a system in which you can import or ETL, as is the word, if you can ETL your data into the system, you can create indices, and it will take time to build them. It will eat a bit of space to store them, but then the queries are much faster. So this is what you get in a system like MongoDB. And then data store, that would be the definition of MongoDB. Why do we say data store and not database management system like you would for PostgreSQL? It has to do with the fact that MongoDB doesn't have a query language. So it's a more primitive form of database management system. It's missing a few features to call it a full-fledged database system, right? So this is why we have the term data store for that. A data store is a bit on a lower level than a full-fledged database management system. And finally, querying. And then you're going to tell me, yes, but we already have SQL to query. And you're right, we already have SQL, and it can do a lot of things. It can deal with tables. To some extent, it can deal with data frames. But I would like to show you first the limitations of SQL, why it's not good enough. It was not designed for that. It's basically as if you would, for example, you have a washing machine and you have dishes to wash, and then you say, okay, let me put the dishes in the washing machine, right? Because it's just for washing stuff. It's the same with SQL. SQL was designed for tables, not for trees. So the moment you want to query trees, SQL is no longer the right tool. You're basically abusing it if you try to use it for trees. So this is the intuition that I would like to give you, right? So let's get back to the fundamentals of why query languages in general. So the idea of a query language like SQL is that it protects the user from all the complexity of the physical level, the computers and so on. So you have a language, SQL. All you need to do to write SQL is understand tables. It has rows, it has columns, it has primary keys and so on, and then you write SQL. Physically, it doesn't really matter while you execute it. Could be PostgreSQL on your laptop, could be even on top of HBase. There is Hive, that is a system that brings SQL on top of HBase for data warehousing. You can also do it on top of Spark. Remember Spark SQL? We do have the ability to execute queries on top of data frames in Spark. Like this, for example, right? If you wrote a query like this, select true from input where bar equals foobar, internally, these are the RDD transformations that you would get, right? Do you see who agrees it's the same, right? But I think probably many of you would find the SQL version simpler than the complexity of what is below. And again, the reason is simple. On top, you have a query language, and below you have an application programming interface. That's not a query language. That's the reason why it's more verbose and on a lower level. It doesn't mean the application programming interface is useless. On the contrary. In fact, this is how people implement SQL. They actually use that application programming interface to implement SQL. But they are the only ones who should touch it. You as a user, you should actually be using SQL or a query language. Okay. So this is the same query, but here executed with data frame transformations, which are higher level, but still an application programming interface. But this works because the data is homogeneous, meaning that every row looks the same, and it's normalized. You don't have any nested structures, it's all flat, and so on and so on. So it's the beautiful world of relational tables where SQL is at its best. In fact, this is 80% of the cases in practice. If you have in the future a project, a semester project, a master's thesis, a PhD thesis, and so on, and you have data and you need to query data, it's very highly likely that a relational database management system, tables, and SQL is all you need. It's very likely. Be very careful before rushing into big data technologies and so on. Many people, all they need is SQL because their data is actually nicely fitting in tables. But if it doesn't, then you can consider going with nested and heterogeneous data to accommodate better for your use case. But again, I insist, in many cases, SQL is all you need. It's a really nice language. It's 50 years old. There's plenty of systems, some of them free, that work on that. But here is when it breaks. It breaks when your data is not flat and homogeneous, not a relational table. You might have extra values in some rows, extra columns that don't exist on the other rows. You might have missing columns, missing values. You might have invalid values. Maybe you have integers in a column everywhere, but in one of the rows, it's not an integer. It's an array of integers, for example. So that would be invalid if you would try to validate it against the type. You might have nested values. You might have arrays of objects nested in some columns that are actually arrays of objects are basically logically equivalent to tables. And so you have these nested values, and that breaks the first normal form because that's, again, not a table. When any of this happens, or sometimes all of that together, we say that we're looking at nested heterogeneous data sets as opposed to flat homogeneous data sets. These two adjectives are very, very important. It's very important to understand if you have a data set, if it's nested, if it's heterogeneous. Okay? And if it's nested and heterogeneous, by now, I hope that with all the weeks we spent on that, you understand that it's no longer a table, it's a collection of trees. Basically, each tree would correspond to what was a row in the table. Instead of having a collection of rows that all look the same, have a collection of trees. Okay. However, I told you that if you use Spark and you try to import a data set, like let's take a JSON lines data set. So it's a huge files or maybe plenty of files with one JSON object per line. You can actually open it with Spark, and you can even try to open it as a data frame. So you know that data frames only work if you have a schema. So if you have a JSON lines data set, you don't have a schema. But the good news is Spark will do it for you. It's going to go through all of these objects, and it's going to try to find out the schema. It's going to infer it or guess it. In many cases, it works. If your data looks really nice and there's patterns, and every time you have the key foo, it's with a string. Every time you have the key bar, it's an array of integers and so on. Then Spark will infer the schema correctly. But let's try to fit this into Spark now. Let's assume this is here, the JSON lines data set we have. It's very small in that case because, again, it needs to fit on a slide. Look how it breaks. If you were to try to infer a schema, for name, if you look at the first documents, you might think, okay, that's an object. It has a key first that is a string. It has a key last that is a string too. It works for the second, for the second object as well, the third, the fourth, the fifth, the sixth. So it works everywhere, right? So it seems like you're on the right path if you try to validate it as an object, first string, last string, and then bam, breaks. That doesn't work. Here it's a string. It's broken. So this is what's happening right here is in fact what I put here. You have an invalid value. So what do you do? Well, it doesn't fit in a data frame, obviously, right? Because either it's a string or if it's an array of objects, it's an object, but it cannot be both. So that's broken, that's heterogeneous. And there is another instance where that happens, it's countries. Look at countries. If you look at the first objects, the first three, you will see it's an array of strings, right? But look at the fourth one. It's not an array of string anymore, it's a string, US. And then UK again, it's a string. Then it's an array of strings again. And then you even find a null in the last one. So you see it's heterogeneous. Now, the null wouldn't have been such a big deal, right? In SQL and in relational databases, we can deal with nulls, right? We can put nulls in some cells and that's fine. But in the case that we have both strings and arrays of strings, then that's problematic. But there is something that I almost would say is worse. If you fit that in Spark, it will not reject it. You will not get an error. You will get a data frame. But look at the data frame you get. You get a data frame with a column name that is a string, I insist, a string. A column name, a countries that is also a string type, so a string. And then number then is an integer. Number, actually, we added it just because one object had this number field and all the rest is null. Okay, but this one worked, it's an integer. But look closer to name string, what is actually happening here. Because you could tell me, okay, that's not a string, that's an object. It's not an object, it's a string. This is the string open curly brace, quote first, quote colon, quote Albert. That's a string here. That's not an object. So what's happening is that it's forcing the serialization of all the things that are in there. It's an object and array and so on. It's just forcing it into a string and serializing it as a string everywhere. So what happens is that the user, now you need to work with this data frame. You have strings everywhere. And here it's the same. This is not an array of strings here. This is a string. This is literally a string with a square bracket, quotes D, quote, blah, blah, blah. That's a string. As a user, that's a nightmare. Because now, imagine you try to write a query on that. Imagine I ask you, return all the people for whom name is an object, and the last name is Einstein. How do you do this when name is a string? Well, it's the burden is on you. You are going to have to write code in Python that takes that string, tries to parse it as JSON. If you manage to parse it as JSON, you get a Python dict, basically a Python dictionary, then you can look at for last. But all of that complexity to try to parse as JSON and find last and so on, it's on you as the programmer. Basically, Spark is saying, fine, I'm accepting your heterogeneous data, I'm putting in a data frame, but now it's up to you to deal with that garbage. Right? So this is basically the idea. And this is why there is a limitation of the system with data that looks like that. For whom is that clear? Right? That we are reaching the limits of what SQL can do. And this is a serious problem because it means that a lot of people through the entire world are actually spending a lot of time writing all of this special casing of these things manually, even though it should have been done by the database management system. Okay. All right. So this is on the data, the fact that it pushes to you as a string. But even if that doesn't happen, even if your data actually doesn't have any type impedance mismatches and everything is the same type, you might still have nested data. So let's now look at nested data, even though it's the same type everywhere. So technically, it would fit in a data frame. So then what happens is that you end up with queries where you have to add lateral views, and they are so complex that even I make mistakes. For example, I think 2 weeks ago, when I wrote some examples with lateral views, I didn't even put it at the right place compared to in the exercises. And I fixed these slides, by the way. But basically, this is very complex to read, right? So you're kind of looking at a table, and then you have a nested array. So you need to open the array and create a view on the side, and you might even do it multiple levels. And you end up with queries that look like this. This is SQL, of course, it's a query language. It actually works. But then you might easily end up with queries like this for more complex use cases. And the query like this, it's actually not such a complex query if you formulate it in English. It's actually looking for let me help by looking at this other one here. It's actually looking at the top committers. You basically look at the GitHub data set. You look at every event that happens in GitHub, and then you search for the top committer and then return its commit. So the query in English is return the commits by the top committer. This is SQL to do it. This is like super complex to write. And there is a reason that SQL was not designed to deal with nestedness. So you end up having to write all of these to kind of find the top committers and then feed it back in some way and so on and so on. So it works. It doesn't break, it actually works, but it's very complex to understand. And so this is why we have languages that have been invented more recently that are specifically tailored for dealing with nested and heterogeneous data. So the one that we are going to use is JSONic, because I was involved in that one. It was one of the very first ones. But JSONic is also actually following a standard. You might have heard of the W3C, right? They are the ones that also standardize HTML, XML, and so on and so on. And one of the standards is called XQuery for XML. It was designed by plenty of smart people. There were people from Microsoft, from Oracle, from IBM, MarkLogic, so plenty of companies, very smart people. Some of these people are actually also editors of SQL. So they also have a lot of experience on SQL. So all of that experience that came from SQL went into xQuery. But the problem with xQuery is that it scares a lot of people because it's XML. And somehow, there's no reason for it, right? But XML looks scary somehow. And JSON was emerging, has been emerging in the past few years. So what happened is that as part of the discussions of the working group, we wanted to adapt it to work with JSON. And this is how JSONic was born we carried over xQuery to deal with JSON data and making it simpler. So this is what JSONic is. Now, in the meantime, a lot of other people figured out that you need a language to query JSON, and now there's 30 plus languages. But the good news is that they all more or less look alike, right? So they do it well or less well, but the features are more or less the same. So if you learn one, it's going to be very easy to learn any other one. I cannot tell the future. In 5 years, in 10 years, my hope is that it consolidates, that just like SQL, we reach a standardization of querying collections of trees for document stores, for data frames, and so on. But now we are just in the situation today that there are 30 languages. And in fact, JSONic is already based on a standard because the 95% of it comes from the W3C. And again, there are people from Microsoft, Oracle, IBM, so plenty of very knowledgeable database people who design all of that in details. All right, so this is why I'm going to show this one to you. I'm going to contrast it with SQL and show you all of its secrets. Okay, so there is a data set that we love to use for the exercises, but also the exam. So we've been using it in many exams in the past. The reason we like this data set is that it's both nested and heterogeneous. It's actually an archive from GitHub. It's actually bigger than that, the entire archive. We just picked one with 2.9 billion events. It's 7 terabytes, so that's actually big data. And if you look at it, it's there is no real schema that all objects follow, and it has to do with the fact that it evolves around every year, and so some of the fields are removed, some other are added, and so on. So if you look in total, you will find 1,300 attributes that already doesn't fit anymore in a relational table because that's 256, typically the maximum. But if you look at a single object, it's not going to have 1,300. It's only going to have 100 of them. So you see that this is already looking heterogeneous. And it's nested because you see there's an array of objects here, there's a nested object, and so on. And 10% of the path, what we mean with path is, for example, repository.name is a path, right? So the locations in the object, 10% of them have mixed types, meaning that at the same place, here you have an integer, here you have a string, here you have an array of strings, and so on. So this is heterogeneous. So we love it. Of course, we are not going to give you the 7 terabyte version at the exam. We have a much smaller version. I think that's 80 megabytes or something. So something that fits on the computer and that is much easier to handle, right? But this is the idea. Okay, so this is our use case, and there are many, many others. And the idea is that a language like JSONic acts just like SQL as a data independence layer. It's a high-level query language, and you execute it on top of anything. It can be on top of Spark, as is the case for what we will do in the exercises and exam, but it would also work on top of HBase, on top of MapReduce. It could work on top of MongoDB as well. You could actually also make it work on top of MongoDB. And this project, so the implementation we'll use is called RumbleDB. It's actually being developed by your predecessors. So there has been 20 students working on it in semester's thesis, in master's thesis. So it's really a lot of people who worked on it, and now it's stable enough that we can use it in the lecture. That was all part of big data, actually, the way it was developed, because the very first time I taught big data, it didn't exist, right? So this is really something that came with the years. And it's free, it's open source, so you can even use it later if you want, even commercially is not a problem at all. Okay. All right. So I have 15 minutes left for today. So let me give you a few more details on query languages. I'm probably already said these things, but just to make very clear a few definitions. JSONic is declarative, functional, and set-based. SQL is also declarative, functional, and set-based, right? So what does it mean? Declarative means what versus how. It's the difference between cooking at home and going to the Mensa. If you cook at home, that's basically Python or C++ or Java, right? You take the ingredients, you cut them, you put them in the pan, and so on and so on. The what functional language is you go to the Mensa and you ask for the veggie menu. That's the what. That's declarative. And the cooking is basically happening in the kitchen, but you have to pay for it, right? So this is the difference between the what and the how. It's like a recipe versus just asking for the menu that you want. If it's a what, that's a declarative language. Second, functional language. A functional language that actually comes from the notion of mathematical function. It's the fact that when you have a query in that language, it's actually function calls in mathematics, just like you can have, I don't know, x squared or and so on. These are all functions. And the idea is that in a functional language, you manipulate values. Instead of being numbers, it's going to be tables or it's going to be collections of trees. So these are the values you manipulate. You can still model them as math. And then a function takes these tables or these collections of trees. It might even take several tables or several collections of trees, and it's going to return a table or a collection of trees. So this is called the functional language. Instance of the model just means a table or a collection of trees, right? You have a model, can be the relational model, can be a NoSQL model, and so on. And you have an instance of the model, that's the values you manipulate. So everything you do in the language, it's declarative, but it's also functional because you manipulate these instances. So basically, in SQL, you just have tables flowing around. In JSONic, you have collections of trees flowing around, so to say. A misconception about functional languages is many people think that, you know, when you have a function in math, you have these parentheses, right? F of x, and then you have the parentheses around x. When you have function in a programming language, you also typically use parentheses for the function call and for declaring the function. And so a lot of people think, okay, in a functional language, then you have function calls. But no. In the API, yes, maybe. If you look at the Spark API, if you look at the MongoDB API, you will see parentheses. But in a real functional language that is a high level, the functions are actually hidden. You don't actually see the parentheses and the calls and so on and so on. See, for example, look at SQL. There is no function call in there. There's no parentheses. And yet, you still have functions because what functions do you have? You have a projection function that projects to foo. You have a selection function that selects bar equals foo bar and so on. But the language here is so nicely and intuitively designed that you barely see them. It looks intuitive to the user. But behind the scenes, you have a selection function and a projection function. That's exactly the same with JSONic, right? If you look at this query here, there are parentheses, yes, but these are not for functions. It's only just like when you use them for addition and multiplication to overwrite the precedence. Okay. All right, so this is what functional means. For whom is that clear, this idea of functional? Okay, and again, it's functions, but if the language is well designed, they will be hidden from the user. It's designed in such a way that for the user, it's intuitive. And instead, we talk about expressions rather than functions. And finally, the third word, set-based language. It means that in many languages that are not set-based, you process one value at a time. If you use, for example, Python, maybe you have a function that's going to return an integer, an int, or a float, or a string, or maybe some dict, and so on and so on. But it's only going to be one value. In Java, you might also return int, short, bytes, or maybe a string, or maybe an object that is an instance of a class. It's only ever one thing. In fact, it's going to be a pointer. If it's a complex thing, you just return one pointer. Even if you have a list in Java or a list of Python, it is still one thing. It's still a pointer to a list and so on. But in a set-based language, every value is actually plenty of values. A table is not just one table, it's a collection of rows. It's 1,000, it's 1,000,000,000 rows, right? In JSONic, it's going to be billions of trees or billions of items, as we will call them. So then you could tell me, yes, but in Java and Python, we still have lists. Yes, yes, but the list, maybe you can fit 1,000 or 1,000,000, but 1,000,000,000,000, that's not gonna work. You cannot fit 1,000,000,000,000 values in a Java list or in a Python list because the language was not designed for that. But if you have a set-based language, you can actually have trillions or even quadrillions of values at a time returned by a function because the language is made to be parallelized and spread over a cluster, right? So this is it. And overall, you will see it's a bit like SQL, but even extra. It's like playing Lego. You basically, I'm going to give you the pieces, just like I did for JSON, right? I told you there's objects, there's arrays, there's strings, there's numbers, there's booleans, and there's nulls, 6 of them. For XML, I told you there's elements, attributes, text, and so on. These are the building blocks, then you assemble them. For JSONic, it's the same. There are also building blocks, expressions. In fact, I think there are 37 of them. 37 is actually not such a big number. It's like a catalog of things, just like the Spark transformation. So I'm going to show you the 37 building blocks. And then it's like Lego. You just have plenty of copies of these blocks and you build your huge masterpiece with that, right? You can assemble queries. Okay. So the implementation we have, RumbleDB, it works on S3, on HDFS, on HTTP. You can even download from HTTP in your query, on your laptop, the local file system, on Azure Blob Storage. You can read text, you can read JSON, CSV, Avro, Parquet, Roots, which physicists like at CERN, libsvm for machine learning, and so on. And for those of you who heard about the Lake House, which is advertised by Databricks and now several providers, is that JSONic is ideal for a lake house that basically does relational tables, data cubes, heterogeneous data sets, machine learning, and so on. So all of that integrated in a single system, right? And yeah, so of course, in the lecture, we'll not cover all of that. I think we'll probably use your local file system and JSON a lot on your laptop. And then there will be experiments with Azure as well, with Azure Blob Storage. So this is a thank you page for all of the people, so your predecessors who have written thesis with me and contributed to RumbleDB. So this is, I'm really, really thankful to all of them because this is how we built that system and we have it for you. So what's the best way to present what RumbleDB is or what a system that implements a functional language is? I think the best way to describe that is that it's a calculator. So on a calculator, you just type formulas with 1 + 2 × 3 and so on and so on. So you type them. In one of these simple calculators, you just type on keys, right? But then you also have calculators on computers where you can actually type it as a string, right? You just type your expression, press return. So that would be something like MATLAB or Maple for those who knows MATLAB, Maple, these systems, right? These are also complex calculators in a way, right? So JSONic can also be seen as a language for a data calculator. In fact, 1 + 1 is a JSONic query. It works. Type it in the shell, 1 + 1, it will answer 2. Works like a calculator, right? This works too. 3 + 2 × 4 going to return 11. That's also JSONic. So you see, you already know JSONic. If you type 2 smaller than 5, that's also calculating whether or not 2 is smaller than 5, and it's returning true, right? So 2 smaller than 5, that's also JSONic. You can actually type 2 smaller than 5, and you're going to get true. But it's a complex calculator because it has many bells and whistles that actually make it very powerful. This is another bell and whistle of JSONic. It's the let. It's a way to bind the variable to some value and then use it. In fact, JSONic is not the only language that does that. There's plenty of other languages, like who actually heard of Haskell or OCaml or any of these? Some of you. So let should not be unknown to you. This is a feature that many functional languages actually have. So in that case, the variables, they have these dollars. This is how we see that these are variables. It basically makes it easy to see. There's other languages like Perl that use dollars for the variables, right? It's not the only language. And so we say that $I is bound with the value 2, And then having done that, having said that $I is 2, then we compute $I plus 1. So what is that? Well, we replace $I with 2 and we get 3. Okay. For whom is that here? Okay. Now you're going to ask, why this colon equal thing that looks very complex? Well, that's a pedagogical thing. Because if we had just an equal sign, that might be confusing to some people, right? One of the things that we teach, especially in other departments, is the difference between an equality test and an assignment, which is not the same thing, right? So this is in order not to confuse equality with assignments, that we use this colon equal. And this colon equal is basically saying it's an assignment of 2 to the variable $I. Okay. This also works. This is JSONic. So if you type square bracket 1, 2, 3 square brackets, that actually works. It's going to return, well, the same thing. So you see that this calculator is not only able to return numbers or Booleans and so on, it can also return JSON. It can return JSON arrays. So in that case, that works. This works too. And in fact, the secret, you can take any JSON value, an object, an array, even super large JSON array object, you put it in RumbleDB or in JSONic, it works, it just returns itself. So you already know JSONic, a subset of JSONic is any well-formed JSON is a correct JSONic query that just returns itself. But of course, if it were only that, that wouldn't be very useful. And so this is why we have, of course, some more dynamic stuff that allows you to calculate and transform this JSON. All right, so here's an example of the sort of things you can do, right? So this is no longer JSON, right? You can take a JSON object, literally, and then .foo, and it's returning 1. This is JSONic, that actually works. That's another one that basically takes an array 3, 4, 5, and this double square bracket here, it extracts from position 1, right? So JSONic, because the goal is that it's usable also by non-computer scientists, we start counting at 1, which is more intuitive to many people, right? So just a matter of convention. So 1 is the first position, so we extract the value 1 from the array, and that returns 3. This is a more complex query, and you can again think, this is, so first it starts with some JSON, it's an object, foo associated with an array of integers, .foo returns the array 3, 4, 5, we extract 1, so we get 3, and plus 3, 6. Who understands that this returns 6? Okay. It's just a calculator. Could be plus multiplication and so on, but we also have dots and square brackets and so on. It magically calculates. So it's basically a JSON calculator, a data calculator, right? And I said it's set-based, so it can also return sequences. In that case, if I take foo, .foo, that would give me the array 3, 4, 5, and I can unbox the array like a Christmas present, right? So I can put these square brackets there. It opens this array 3, 4, 5, and then returns 3, and then 4, and then 5. And that actually goes to trillions if I want. I can actually return trillions of values. Okay. 1 to 4 is an example of query that returns the range. So 1 to 4 is returning 1, 2, 3, 4, and so on and so on. Okay, so I'm going to stop here. I think I've already, that's the appetizer, basically, that it's a data calculator. And next week, I'll just drive you through all the features of the language. I'll tell you a few words about the implementation. And then you'll have exercises and you will be able to run it on your laptop, and you will also have it on exam day. But again, you can exercise on it. We'll give you the data sets before the exam. You'll already know in advance what data sets you will have, and then you can exercise. All right. So that's it for today. So thank you very much, everybody, and we'll continue with that next week. Have a good day. Enjoy the exercises.